Welcome to episode 9. We're going to talk today about elements. We're going to talk about elemental or ionic bonding, various kinds of bonding, and then we're also going to talk about minerals today. So this is going to be the stuff that everything's made out of on Earth. So to begin with, here on the first page here, in fact, this is from a museum that shows you some of the various minerals and their various beauty, I guess you could say. It's Earth is made out of astounding materials, and these are some of the ones that human beings like to think are very aesthetically pleasing. So that's the first title slide there. Next, when we think about minerals, we also think about the sort of things that we've used in the geologic past. And when I say we, I'm talking about ancient human beings mostly. And so, and even from ancient times, we've known about a lot of these various things. Zinc was known since ancient times. They used a mineral called sphalerite, and sphalerite was actually smelted to drive off the sulfur in that compound to make pure zinc. And so zinc has been known for a long time. Obviously gold. Gold was a standard for many of the early civilizations. They made jewelry out of it. They used it to purchase things and everything. And silver is the other one, of course, right? And so I'm just going down the list here, in fact. And so I have images for all of these. So 1 through 12 here. These are all ancient substances that have been known. And today, several of these, in fact, so like copper, gold, silver, those are all things that in fact happen naturally. Carbon, of course, too, right? So carbon is just made out of C, right? So that's the symbol we use to indicate carbon. But that's been known from like ancient firewood, right? You know, when you burn something, you're going to turn it either into ash or you're going to turn it into charcoal if you cut down the oxygen amount in it. And so arsenic's been known for a long time as well. And then sulfur, of course, sulfur has little yellow crystals, and people knew that from hanging around in volcanoes and climbing mountains, as human beings are apt to do, you know, when they're surrounded by mountains. Tin has been known for a long time. In fact, the whole idea behind the name of Britain stems around the tin mines that were there back during the Bronze Age, and so Britannia. And so iron, of course, iron is known from the second sort of stage of human civilization development. And so they made tougher materials, tougher instruments, essentially, of war or for farming and things like that. And so Iron Age was one of the things that people recognized. And then, in fact, even when you didn't have access to the ability to smelt iron, people would find it in meteorites and things like that, the stony iron, not the stony iron ones, but the nickel iron meteorites. And so mercury's been known for a long time, and so it was known as quicksilver, right? So it looks like silver, but when you try to touch it, the beads like scatter, right? And so, and then lastly, antimony on here. So those are all things that have been known for ages. Okay, so, and these are kind of like the things that we use over here still these days. And so, in fact, today we're even more focused on things that are called critical minerals. And so minerals are going to be the ultimate end of this lecture. In fact, we're going to talk about how you would identify minerals. But first, we got to start with the elements, because everything's made out of something, right? And so the guy who started organizing these elements into categories, his name was Dmitry Mendeleev. He was a Russian chemist. And so when people first began to fill in the table of what we knew as elements, there were dates associated with each one of these discoveries. And so people published on it, right? So we had printing presses, and so people began to say, oh, I found this mineral, or I found that mineral. And it was Mendeleev who actually organized it into a table here. And so he gave us things like group 1, group 2, and that's actually his diagram for showing us these various groups of different minerals, in fact, different elements that would combine to form minerals at some point. Now, many of the ones that you saw on the last slide, those are what we today regard as natural or native elements. And so, but these other ones, in fact, had to be separated out in order to identify them. So many of them combine with other ions of other elements in order to make compounds. And so An atom is the smallest indivisible part of an element. And today we know that there's 118 elements. And they all have names now. So when I was a student in your position, not all of them had names yet, and they just gave them letters to identify them because they belonged to certain groups or families, if you will. But atoms are the smallest part of those elements, those 118 elements. Those are the only ones we know of at this point. There may be some situations where in the future, there may be additional ones found that are going to be even heavier than the ones that we know today. But we know the lightest very well, and we know some of the heaviest ones, okay. And then many of them don't even occur in nature, okay, so they have to be manufactured. And so that's some of the highest numbers, in fact, of the atomic mass for these things that we don't see them in nature so much. So atom's the smallest indivisible part. They're made out of other things, right? So an atom has a nucleus and an electron cloud surrounding it. And so that cloud may consist of nothing more than 2 electrons spinning around on the outside of that nucleus. So the nucleus is in the center and the electron cloud is around that. Typically it's going to be 2, but sometimes you can even lose the electrons and you're left with something that doesn't have electrons. And those are what we're going to call ions. And so ions have gained or lost electrons in order to form a more stable sort of substance, in fact. But the nucleus, in fact, can have up to 200, 300 particles in the center of that. And those are all going to be things like protons and neutrons. So by definition, the electrons have a negative charge. And so a negative charge is an electron, right? It hardly weighs anything. So it's just out there spinning around this nucleus. It's attracted to the inner part. It's attracted to the protons, in fact, inside of the nucleus. And so that's why the electrons are attached at all, right? So you have to have that positive and negative attraction in order to make things work. So the nucleus and the electron cloud exist. And so in the nucleus, we have the protons and the neutrons. The protons have a positive charge. The neutrons have a neutral charge. And today, we know that there's inadequacies in the way that we explain this to people, because in reality, many of these things are actually composed of quarks. And so quarks, in fact, are smaller bits and pieces that make up protons and neutrons. And I'm not going to hold you responsible for any of that because it gets out there beyond what we want to talk about in geology. So that's, if you want to learn more about that, you could take a chemistry course or take a physics course and learn about quarks. But quarks are kind of unusual. And we also know that when there are arguments about, is that something that behaves like a wave or is it something that behaves like a particle? And we know that particles can sometimes appear to be waves and sometimes they can have the appearance of particles. It all depends on when we measure them, right? So if you're interested in that sort of thing, I highly encourage you to take a physics course or to take a chemistry course, and you'll learn more about the double slit test hypothesis. And so, in fact, many of the things that we today recognize are actually fields as opposed to being actual particles. And so field theory is something that's really important. And it's all based on mathematics, frankly. So it's very important to understand it. And so if you go to YouTube, listen to guys like Brian Greene, or if you listen to guys Neil deGrasse Tyson, these are all folks that are knowledgeable in particle physics or in field theory. And so anyway, for our benefit, just simply putting this into context, we want to talk about things like atomic number. Atomic number is what makes an element an element. It really is based on how many protons are in that nucleus. And so the protons in the nucleus determine the atomic number. Now, the atomic mass combines both the protons, positive charge, and the neutrons, which have a negative charge. And so the atomic mass tells us how heavy that nucleus is. And so, in fact, if you took something like uranium has a couple different ways, well, more than 2 ways that it can form with different masses, but it's always going to have 92 protons in it. It's always going to have 92 protons. The variable number of neutrons in that, we call those isotopes. And so you're going to learn a couple of I words today. One of those is ions and one of them is isotopes. But isotopes just tells you that there is a variable mass to each one of these sort of, well, entities, and they behave differently, right? And so with uranium, it's 235 and 238 are the most common varieties. And so that's the mass, uranium 238 or 235. Those are masses. But the atomic number is always the same. It's always going to be 92. So atomic number of protons in the nucleus. The atomic mass, the number of protons plus the number of neutrons in it. And the electrons, they don't always match the number of protons in the nucleus. And so, in fact, even though they have a negative charge and they're nearly massless, they have a little tiny bit of weight, but it's very, very small. I mean, not like really small. By convention, for us anyway, in this course, we assume or we assign a weight to protons, we assign a weight to neutrons, and each one of them is going to be equal to 1. And so that's why we get 238 particles in the nucleus of a uranium atom. And so, but 92 of those are going to be protons. So the atomic mass, the number of electrons around doesn't always match. And so, but anyway, it was Mendeleev who came up with a chart. So you can see that chart in the next diagram here. So this diagram is really, we call it the periodic table of elements, right? So he came up with the first version of that. And so, on here, you can actually see numbers that are assigned in the upper left to each one of these. That's the atomic number. That's how many protons are in each one of these, and that's what defines that element. And so, for instance, hydrogen, you see in the upper left here, it has 1 proton. That's all it has, right? So it has 1 proton. It was discovered in 1766, and so that is the number that's in the middle of this. So they list the name and the year that it was discovered. And in fact, they even tell you who found it at the bottom there, right? And so that was the year was discovered in the middle part there. And the symbol that we use. So we have a shorthand version for this. So that, we do that so we can do chemical equations and balance the chemical equations. And many of you are taking geology because you don't want to study chemistry. And I realize that, right? So, but we still have to obey sort of like the formal definitions for each one of these. So hydrogen is just abbreviated H. And you get to helium, it's going to be He. That's over on the top on the right-hand side here. So He stands for helium. If we go down the list here, I can actually name off some of these anyway. Well, they all have names on here anyway. So lithium is Li. It has atomic mass that's not listed on here, but the atomic number is 3. Beryllium has an atomic number of 4. And so you can see that. So you can see how they're lined up in rows across here, but they're also lined up in columns. And it's the columns that are really significant. So the rows kind of jump. So you can go 3, 4, and then you have to jump all the way over to boron, which was discovered in 1808 there. And then you go to carbon next. And so you can go to each one of these, and the ones that don't really have a discovery date, they just say it's ancient, right? So those are the ones that are really the oldest that we know of. And so all of these, in fact, go across here. So, but the columns are important. I'm going to go over that in just a minute here. So there's a first column, there's a second column, that's group 1 and group 2 there. And then there's group 3, the scandium and yttrium there. Beyond that is titanium, zirconium, and hafnium. And then some of these that were named more recently here, so like in 1969, they named one after Rutherford, who was a famous chemist who lived in New Zealand, right? And so Rutherford was that guy. He was in Christchurch, New Zealand. Vanadium, magnesium, chromium, all of these sort of things you may have some familiarity with. Well, chrome comes from chromium, right? And other things on here, nickel and cobalt and so forth. And you get over the right-hand side, you can see how they're all green over there. And so they were discovered in the middle part of the 19th century, so in the mid-1800s essentially. So helium, neon, argon, krypton, xenon, and radon. And those are all things that are gases today. We know those as gases. And so if you look at that bunch on the right-hand side there, those are all things that don't like to interact with anything else. And so if I said that the electrons don't always match up, typically in that column they do. And so because you have two protons in the helium nucleus, you also are going to have two electrons spinning around it, essentially. You can get a variable number of neutrons in that, however, but typically you're going to have two protons in it. And so typically it's going to have four particles in the nucleus, and so it's usually going to have two neutrons and two protons. But every once in a while, under certain circumstances, you can only have one neutron in there. And so that's He plus 3, they call it, I think it is, or He3. So anyway, that is the mass sometimes of these things, but typically helium is going to be a mass of 4. Hydrogen's typically going to be a mass of 1, okay? So just over 1, in fact. And so there are situations where you can even have... Well, anyway, it gets a little more complicated this way. And this is not a chemistry class, so anyway, thanks for paying attention to this anyway. So we have this periodic table of discovery. That's when these things were all discovered. I'm going to page on to the next one here, which shows you another version of this diagram, but it doesn't show you the time when these things were actually discovered. But it gives you all of the abbreviations on here. So as I go down from the left-hand group 1 column there, hydrogen, lithium. Na is sodium. In fact, it was named for the natron, which is what it was originally regarded in the ancient literature, right? So when people talked about natrium or natron, that's what it is. It's sodium. And then potassium, it was known by a different name, but today we abbreviate it with that ancient name for it with the K. And so the K is what that stands for. It stands for potassium today. Rubidium is Rb, and then cesium is Cs, and then francium is Fr at the bottom of that. So that's the entire first column there. And if you look at the next column, that's beryllium, magnesium, calcium, strontium, Sr, strontium. Ba is barium. And you're going to know some of the minerals that are actually composed of barium. There's a barium sulfate that you're going to learn. And the mineral name is actually barite. And so we'll talk about what a mineral is in just a bit here, but it's barium sulfate that is barite. Ra is radium. Radium is what Madame Curie was studying and when she discovered the radioactivity of radium. So next is scandium, yttrium there. And then that whole series that's 57 to 71, it says there, that's that red line that crosses across the bottom in there. And that's things that typically aren't found too much in nature. Or if they're found at all, it's just going to be the early version. Cerium is one of them that is around as a natural sort of element there. But many of those, in fact, are not. And then the next is a series of actinides. And so that's the green line that runs across the very bottom of this diagram as well. Now, in the blue in here, those are called the transitional metals in there. So those are all metals through there. And you know them as metals too, right? So for instance, magnesium, right? Or manganese is another one, right? Not magnesium, that's in group 2. Manganese is on there. Iron, cobalt, nickel, copper, zinc. Those are all elements that are in those transitional metals there. The next column over here goes all the way to 13, right? That's boron. So boron has the number of 5. So that's the number of protons in its nucleus, but it has an atomic mass of 10.81. Okay, now think about that for a minute. It's like, how do you know that there's 0.81 neutrons? Or, because if you change the number of protons, it's going to change the element, right? How do we know that? Well, it's an average. On average, you're going to have some that are going to weigh 10 and some that are going to weigh 11. And so you take that average. So 81 times out of 100, you're going to have ones that weigh 10 as opposed to weighing 11. And so anyway, that's where that number comes from. So that's the atomic mass. So you got the atomic number at the top. The symbol is below that. Then you get the name of it, and then you get the atomic mass there. And so some of these are kind of important. So for instance, let's take oxygen here. Oxygen has an atomic mass of, atomic number of 8, and then the symbol is O, And then the atomic mass is 16. That means there are 8 protons and 8 neutrons in the center of that. It doesn't mean it's always that way, however. So sometimes there are 16, sometimes it's 17, and sometimes it's even higher, okay? So it has to balance out and equal out to 16 altogether. And so anyway, that's the way that these things are organized. And so the columns are important, and I'll tell you why right now. It's because the ones on the left-hand side here, like on that helium group that's going downward there, right? Or excuse me, the hydrogen group that's on the left-hand side, as you go down there, those things have a tendency to lose one electron. They have a tendency to lose one electron. Now imagine if you're a hydrogen atom and you've got one proton in the center and one electron that's trying to go around that. It's going to be on one side of that atom, one side of that nucleus or the other side. And so it's just orbiting one proton. It's out of balance. It's like having a tire that doesn't have, you've lost a tire weight. And so the whole thing doesn't spin properly, right? And so typically we like to have an even number of electrons in the outer parts of these elements. And so in fact, hydrogen very typically will lose one of its electrons. Now the other thing that happens, in fact, it'll team up with another hydrogen and then they can share that electron on the outside. That's called actually hydrogen bonding. And so H2 is the most common form of hydrogen, in fact. So typically it's going to have a mass of 2, right? But it's combined, right? So it's H2. And you're probably familiar with H2O, right? So 2 hydrogens can team up with an oxygen. The 2 hydrogens have a plus. The oxygen has a -2 charge, and that's why this is important. So if you look on the right-hand side of this diagram, those things are in balance already. Those are called the noble gases. So the noble gases are in that column, that number 18, group 18 out there. Number 17 tends to have an excess electron in its outer orbitals in order to achieve some balance. And so, for instance, if we take fluorine on there, right? So 19 is the common weight for that. There's going to be 9 protons and 10 neutrons in it. But you can't, it's not good to have 9 electrons on the outer part of that fluorine gas, right? So instead what it does, it grabs an electron from somewhere, anywhere you can get it, right? It grabs that extra electron, and because it has a minus charge on that electron, it gives that entire atom a negative charge. And so it has a -1 charge. So everything in the second column N from the right-hand side here has a -1 charge. If you go into the next column there, that's oxygen, and oxygen has a -2 charge. And so that's the way this works. It's all set up that way. And Mendeleev knew that, and so he organized these things in order to show that, okay, on this side over here, we get a +1. On the next column in, where beryllium is on here, that's a +2. And over here on the left-hand side, well, that's balanced. That's the noble gases. And then you get a -1 in the fluorine group there. And then you get the oxygen group there, and that's a -2. And so that's the way this whole thing is organized. And so you've already learned that isotopes, in fact, are elements that have a variable number of neutrons in their nucleus. Isotopes have a variable number of neutrons in their nucleus. Ions have a variable number of electrons around the nucleus. And so the ions on the left-hand side, that's the helium side over there, those things are called cations. And so cations have a positive charge because, hydrogen's going to lose its electron in order to achieve stability. So it's a +1 charge. If you go to the right-hand side now, in that second column, that's a -1 charge, right? Oxygen's -2. And so there's a plus side on the left-hand side and a minus side on the right-hand side, excluding the noble elements there, the noble gases there. And so everything in between has various charges. And so those things are all called ions. So that's the difference between an isotope and an ion. Isotope, variable number of neutrons. Ions, variable number of electrons in the outer shells. And so you get pluses and you get minuses. And so those are the way that these things combine with one another. And so that's how they form compounds. So compounds are where you take part of one element and part of another element, you add them together, and they can get pretty complex after a while, right? Because then you can add water to it. You can do all sorts of things to it, right? Those are compounds. In chemistry, that's what we call them. So on the next slide here, so covalent bonds are where you actually have not the pluses and minuses that get attracted to one another, but you actually share the outer shells of the electron cloud on the outside. So what it does, it kind of fulfills that imbalance that may be missing an electron, may have an extra electron. So if you share those together, it forms another type of bonding that we call covalent bonding. And so it makes it stable, essentially. So it's like it's combining different ions still, but at the same time, it's actually making that imbalance so that it's balanced. And so they can either be strong or they can be weak. Now, for instance, in diamond, they're very strong. In many other covalently bonded substances, they tend to be weak. But anyway, there's some examples on here. For instance, the CH4 is methane, right? So you have 4 hydrogens around a carbon, and you can share electrons that way. So the 4 excess electrons that are in just single orbiting electron around a hydrogen would be shared then with the carbon, and you can actually form a covalently bonded substance that way. So CH4 there, you can see as an example of that. I give the definitions for these things, so I'm not going to go over it in great detail, but isotopes have different masses of the same element. Electrons orbit the nucleus there. Electrons can have different energy states, so they can pop up and down, essentially. They have different ways in which they actually orbit the nucleus as well, so they have different shapes. And that's what that sort of middle layer is on the left-hand side here. It shows you the various kinds of, they can form like a globe around it. They can form a figure 8, and that figure 8 may have 3 different axes on it. And so you can actually get like, an A, B, and C axis on these electrons, the way they give them different names in that. So I think it's the S, and then you get the S, P, D. I think there's a whole bunch of different orbital names. We're not going to get into that in great detail. So, and you know what atoms are, right? So atoms can lose electrons or gain electrons and become ions. And if they gain neutrons, they're going to become a different isotope. But by definition, I told you what a cation is. Cations have a net positive charge. Anions have a net negative charge. That's because they picked up extra electrons. So over here on the right-hand side, you can see the various ways. Those are called Bohr models for these elements here. We know in reality it's not that way. These things, we've never really imaged some electrons. We've seen the nucleus of some elements, but we typically, you can only look at the cloud for a short period of time, and so scanning electron microscopes are able to do that. Scanning tunneling electron microscopes are able to do that, but very rarely do we see things like that. And so the metals are the easiest ones to image, and people were able to do that since the mid-1990s and so forth. So, but here's some of the Bohr models for this, and you can see over here, for instance, on helium that it's balanced with 2 electrons in the outer shell of that element there. Neon, over here, you can apply a charge to it, and it's going to glow different colors, right? Because you're used to neon signs and things like that. Well, that's what you're doing. You're raising the state. It's giving off a color associated with that energy state, and so. Anyway, that is the neon that's below that. And over here on the left-hand side, you can see that that's not going to be in balance on the left-hand side. And so they're going to want to gain or lose electrons. So lithium will try to pick one up, and hydrogen can combine with another hydrogen to balance it out. So we have things that are associated with the combinations of elements. We're going to call those things, you can call them a substance, but we're really compounds, right? So compounds are where you take one element that has a certain charge and another element that has a certain charge. And if the pluses and the minuses can balance out one another, they'll come together. So for instance, in hydrogen, you have a plus charge, right? And for oxygen, you got a minus charge, and so that would balance it out, right? So you get a -2, which would attract 2 pluses from the hydrogen, and so you get H2O, right? So, but it's not ionically bonded as it turns out, right? So because it's a very simple molecule, we don't call that, we don't call it covalent bonding, and we don't call it ionic bonding in the case of water. But in fact, pluses and minuses do tend to attract one another. And so group 1 tends to have +1, group 2 has a +2, group 3s and 4s can have either 3s and 4 positive. And then there's a group of 18 elements that are known as the noble gases. They don't interact with hardly anything, so we call them inert. So in the right-hand side here, I've got some others over here. So 15, 16, 17 can have negative charges. Nitrogen is a -3, oxygen is -2, fluorine is -1. These are all things to keep in mind because we're going to talk about minerals next in here. And so the way they combine with one another is kind of important. And sometimes they can combine with another element and still have an unbalanced charge. And so things like CO3, right? CaCO3 is a common chemical formula for a mineral that we know as calcite. It's the most common mineral that's in limestone, for instance, right? So calcium and oxygen and carbon come together to form calcium carbonate. And so the carbonate is known as what we call a radical. And so a radical still has a negative charge, but it can combine with the +2 calcium. And so the CO3 has a net negative charge of a -2. And so you combine those and you form things like calcite. And so that's the name of the mineral. We call it calcium carbonate in the chemical sense of the whole thing. So sulfur and oxygen can do the same thing as well, right? And so oxygen's a -2 and sulfur is a +4. And so together, if you add them, well, you take 4 oxygens, and so SO4 is a common radical. It's called a sulfate. And so sulfates have so the oxygen part of it would be a -8, and so the sulfur itself would have a +8. Well, it wouldn't be +8, it'd be +6. So +6, it leaves an overall net negative charge of -2 on the sulfate. And so the way we abbreviate that, so if you look over here, like the second line in the third paragraph on this slide, you can actually see where the third line on this, you can actually see the sulfate radical listed there, SO4, with the -2. So the charges are put in the upper right-hand side there, and the number of ions are shown on the bottom down there. So the O4 means there's 4 oxygens there, but only 1 sulfur. So 1 sulfur plus 4 oxygen, you still have 2 unsatisfied, 2 minus charges, essentially an excess of electrons in there that gives it a -2 charge. So that radical goes out looking for something to combine with. And so we typically are going to combine that with a cation, right? That's going to be a +2. And so that's how that works. So Ca is a +2 and SO4 is a -2. And together they come together to form something called anhydrite, in fact. So that's the mineral name for CaSO4. If we attach a couple of waters to that, we're going to know it by a more common mineral name. It's going to be called gypsum then. So gypsum is CaSO4 dot 2H2O. And that's a mineral. So, okay, so that's how you can combine these things with one another, so we can actually form elements with radicals, or sometimes we can just take the elements and combine them together. The simplest one that most people use to illustrate how you can combine elements is sodium, which is a +1, and chlorine, which is a -1. And together they balance each other out because one's a plus, one's a minus. They come together. They're bound very, very tightly through what we call ionic bonding. So ionic bonding on here is going to give us a chemical formula, NaCl. That's sodium chloride. But you may know it by common names like table salt, right? Or just salt, right? Well, there are many kinds of salt, okay? So we don't like to use the word just salt. When we say table salt, that means you eat it, right? And so what it means is that the sodium and the chloride come together and form a compound. That's sodium chloride. And so, and table salt, we actually have a mineral name for this as well. It's called halite. So halite is NaCl. That's the chemical formula for halite. KCl is another one. Potassium has a +1 charge. That's the K. The chlorine, again, a -1 charge. They get together through ionic bonding, and you get KCl. Now, that's a mineral. It's potassium chloride is the chemical formula name for that, but as a mineral, we know it as sylvite. So Sylvite, sylvite, KCl. And so that is another compound that's ionically bonded then, because the plus and the minus come together to do that, that combination. When we get farther into this, then you can see the next one down here is Ca, which has a +2 charge. It's in that second column, right? And then the fluorine, which has a -1 charge. So it's going to take 2 fluorines to combine with calcium to give us calcium fluoride. That's what the chemical name for is, and that's the CaF2 on here. And so CaF2 that's the calcium fluoride, but it's also known to geologists by its mineral name, which is fluorite. And so fluorite is the element, its elemental composition is calcium plus fluoride. So the next one on here is magnesium oxide. And so I'm not going to get into too much detail, but you can see how the +2 and the -2 would balance each other out. So you get magnesium oxide there. And then down here at the bottom, we've got a radical. And so magnesium oxide, below that one is calcium and calcium carbonate, which I've already kind of described for you here. That CO3 is a -2 charge and the calcium has a +2 charge. That forms calcium carbonate. And calcium carbonate has a mineral name that we call it calcite. And so the one below that, in fact, is anhydrite, in fact. But if we put 2 water molecules behind that, we would put a dot behind the CaSO4 and then 2 H2O. In fact, there's 2 waters that combine with CaSO4. So without those waters on there, that's known by a separate mineral name because it has a separate chemical formula. So anhydrite and gypsum are identical almost, except one of them has some water and it's a hydrated mineral. So hydrated means it has some water attached to it as well. But in deep settings inside of the earth, that's called anhydrite because it drives the water off. Burial drives the water off. So the next one on here shows you an example of what it looks like to have ionic bonding on here. And so you can see the chlorine atom is attracted to the sodium there. And there's a characteristic way in which these things will stack. It's like having small marbles and large marbles together, and the pluses and the minuses come together. So one of the things that's important about how minerals form is their ionic radius. And so the ionic radius is how wide that ion is, right? So how big is the ion? Sodium is much, much smaller than what chlorine is. And so you get sodium chloride in this case, which forms this sort of like square structure. And in fact, that's going to affect how the mineral behaves. So we don't usually see anything at the elemental sort of level. We see it when it's preserved as a whole combination of these things all together. And so we have rock salt, which you can go out and mine in places, right? Halite. And so halite characteristically has a square shape to it. That's the planes of weaknesses. Planes of weakness in this mineral tend to line up along those flat planes that run through what you see on the right-hand side of this diagram here. That's the purple and the green there. And so that is calcium chloride. You're going to know this also as halite later on here. And so next we're going to go on to halite right here, right? So we just talked about that. NaCl is the chemical formula, sodium chloride, but the mineral name is halite. And so that gets us to a very important thing. Let's describe what halite is like. Is it solid, liquid, or gas? Well, it's a solid, right? It's a solid, obviously, right? You can see it, you can hold it in your hand. Your hand can't pass through it like it could through a gas, and it doesn't flow out of your hand if you hold it, right? So it's like, so it's a solid. And it has a chemical formula, NaCl, right? it has a crystalline structure that's based on the ionic radii of both chlorine and sodium. When they stick together, it forms this sort of like complex cubic sort of shape, right? And so that's its crystalline structure. In fact, we say it has cubic shape, but it's a crystalline form, right? So it actually has a cubic crystallinity, right? So the crystallinity is its form. And so it forms essentially squares. You probably recognize this actually. So when you look at table salt, like you pour a little bit out on a table, you can crush it. But then if you look very, very carefully, you can see that when you've crushed it, it still has the sharp corners of being cubic. And so that's the way that it breaks. In fact, you're going to know that sort of property as cleavage. So cleavage is the way a mineral breaks. Or if it lacks any cleavage, sometimes it'll just break as a fracture. And so that's where there's no preferred cleavage, in fact. And so, but in the case of halite, we have a preferred orientation where these things are actually cubic in form. And so for minerals, they are defined by the 5 points for the definition of a mineral. This is kind of important, so you're going to want to learn this, right? The 5 parts to what a mineral is. They occur naturally. They have to occur naturally. So it's going to exclude a lot of those elements that were artificially manufactured in experiments. But it also has to be inorganic, and that's a weird term, right? So what's inorganic? Well, it wasn't once alive. And so in other words, if it's once alive, that means it was organic. Okay, so it's living things essentially, right? So this has to occur naturally, but without the help of human beings, right? Or any other sort of animal for that matter. And so, for instance, if we took a seashell, seashells are made out of what we would say, well, some people would say, well, that's made out of calcite, right? Not really. That's its biomineralization, right? So you have to manufacture it within a body, which means it's organic. Okay, so but if it occurs naturally, and you can get calcite that occurs naturally without any sort of organic material, and we could say that, well, that's inorganic then. So naturally occurring inorganic has to be a solid, has to have a chemical formula. In the case of halite here, of course, we just went through that one, but let's take calcite, right? It can occur naturally, sure. Yeah, it can happen as crystals, right? People sell them at rock shows and mineral shows and things like that, right? It's inorganic, if it's a large crystal. Human beings and any other sort of organism doesn't actually make large crystals that way. And so it is inorganic. It's a solid, obviously. Has a chemical formula, CaCO3, right? And then lastly, has a crystalline structure. In the case of calcite, it can have multiple chemical structures, in fact. And so, but there's only one that's going to have a certain sort of like arrangement of those atoms. And so that's its crystalline structure. And we're going to say that it has a rhombohedral cleavage to it. And so the cleavage tells us a little bit about the way that the calcium and the carbonate would stack together in calcite. So that is the definition of a mineral right there. Pretty important, in fact. So now you've learned, just to reiterate very quickly, you know what an atom is, smallest indivisible part of an element. You know that there's 118 elements out there. You know that they have an atomic mass, they have an atomic weight. In other words, so they used to call it atomic weight, but now we call it mass. They have an atomic number too, right? This is the number of protons. The atomic mass is the number of protons plus the neutrons. We know that they can gain or lose electrons. We're going to call those ions. And we know that if you have a variable number of neutrons in the nucleus, we're going to call those isotopes. And so those are all things we've kind of covered so far. We know that the electrons actually spin in a characteristic way around the nuclei, and so those are called orbitals, and so orbitals are outside of that nucleus. And so they're going to gain or lose different electrons, perhaps, to become ions. Those ions can combine in ionic bonding. That's just one type of bonding so far that you've learned. The other variety, in fact, is called covalent bonding. So sometimes you can actually share the electrons in the outer shells. And so when you share the electrons in the outer shell, that's covalent bonding. And so that happens pretty regularly too. The easier bonds to break are typically covalent, however, and so, but not always the case. Let me give you an example of this, in fact, carbon. Carbon, how hard is carbon, right? You're probably going, let me think about this for a minute. So carbon is 12, carbon 12. And so you bond it with itself, let's say. You can turn carbon into something, we know it as a mineral, graphite. Graphite is something that people study a lot these days because it can hold a charge pretty easily. We make silicon wafers out of that sort of thing. So we mix it together with silica in order to make computer chips and things like that. And so the silica wafers are made out of that material. But in fact, you can just take carbon itself and make things like graphite. And so you can grind the graphite up, mix it with glass, and turn it into silicon. And so silicon can then be ground into wafers to use for electronics and things like that. But you can take graphite and put it under lots of pressure, and you can turn it into something called diamond. So diamond is nothing but carbon. But in fact, that carbon is it's the hardest substance known on Earth, right? So carbon is, and there's various levels of how hard it can be, but the hardest substance that we know of that occurs naturally on Earth is the diamond. Just made out of carbon. That's all it is. It's the one single element that defines it. So that is a variety of covalent bonding there. There's no electrons to gain or lose electrons, but it's covalent. It shares those outer electrons outside of the nucleus in order to form these really, really tough bonds in that case. Now, some ionic bonds are easy to break, though. I will point out, like with halite here, halite, you can lick it and you're actually breaking the chemical bonds between the sodium and the chlorine. And so you're tasting, the elements will actually disintegrate as the bonds will break when they're dissolved in water, essentially, or saliva in that case. So you can break bonds by dissolving them in a solvent, right? So that gets us to different kinds of minerals. You know what the definition of a mineral is? It has to have 5 parts, right? Naturally occurring, inorganic, solid, crystalline structure, chemical formula. Those are the 5 parts right there. So among these things, we like to group just the minerals themselves into things that are like, essentially, right? So there's some what we call native elements. And so native elements can occur all by themselves. Like, for instance, gold. You can find a gold nugget. If you find a gold nugget, it's just the gold itself. There may be some impurities and things like that that are attached to it, maybe some sand grains and things like that. But in general, gold only occurs by itself. That's the only thing that it naturally combines with. Now, you do find it highly dispersed sometimes in volcanics and things like that. In that case, they do what they call hard rock mining, and they crush it and try to separate the gold from the rest of the matrix around it, in fact. But in typical, if you have a nugget, that's actually elemental gold right there. The same thing happens for copper. You can get copper where it's just an element all by itself. There are places around the world where that occurs. And so those are some of the ones that were exploited by early human beings. Okay, you go across the landscape, you can take copper, mix it with a little bit of tin, and you can turn it into something we call bronze. And so bronze, the Bronze Age, in fact, gave us some implements that were a little bit stronger than copper. Copper's pretty soft. Gold's pretty soft, so they didn't make anything. And gold's so rare, in fact, and people wouldn't make anything other than ornaments out of it, right? So jewelry and things like that. Other things would be bismuth, antimony, silver, platinum, sulfur, arsenic, carbon, and tin. Those are all things that we call native elements there. Now, at this point in this lecture, I just want to tell you that everything that we've talked about so far is about materials that are found on Earth. And every consumer good is made out of something, except for information, right? So information that's stored somewhere, right? It's stored in your brain. It's stored on computers and things like that. But in fact, every consumer product is made out of something, right? So plastics are made out of petroleum products. Metals, like for instance, even in pencils, right? They're going to have like a metal on them, right? That has to come from somewhere, usually aluminum or tin or something like that, right? But they try to find the cheapest material that they can in order to like capture that eraser at the end of the pencil. And it's got graphite in it, right? And then it has wood, right? So if you can't extract it from Earth, it has to be grown on the Earth's surface. So for oils and things like that, we extract that out of the subsurface, right? So oil wells and things like that. And then also we have to mine things like, so the metals, and we can't drill down really far. They do for some gold mines and things like that. You can get pretty deep for some gold mines and diamond mines as well. But in general, not so much for the minerals. Typically, they try to get them near the Earth's surface because it costs so much to move dirt around or to move rock around, right? And then you have to separate it from the rock, so everything has a cost to it. And that is one of the most important things you should learn, that everything, if you can, should be recycled, because you're actually helping the planet when you do that, so we don't have to have as many mines to, remove mountains and things like that. And it's a pretty tender subject these days, but at the same time, it's like we need to be responsible for being custodians of this earth while we are here, because we have to protect it for the future generations that will exist. And so it's important to recycle, in other words. So, if you recycle paper and things like that, we can turn that into meaningful products like kitty litter and things like that. I think that's what they do locally here. There's a kitty litter manufacturer, I think even locally. They may have closed shop by now, but it happens in other places as well. So you can recycle paper as well. Even like copier paper is made out of recycled paper, a lot of it. Okay, so I'll get off my soapbox here, and we're going to talk next about the different other mineral classes. We've only talked about one so far. So one of the classes is the native elements. The other ones are pretty important as well. So silicates, that's the number one rock-forming mineral that there is on Earth. Most of the Earth is made out of silicates, as it turns out. Almost 3/4 of the Earth, in fact, I would say, is made out of silicate minerals. And so those are things like quartz, feldspars, micas, pyroxenes, and amphiboles. I didn't add on here, actually, olivine is another one that's really important as well. So olivine is what you find in the mantle. And so, anyway, those are all things that are silicate minerals. They're actually based on the occurrence of silica and oxygen bound together. So the simplest of these is quartz. It's SiO2, that's the chemical formula for it. But the feldspars have a much more complex thing, and they actually incorporate cations into their structure. And the micas as well, right? So the micas would include things like muscovite and biotite. Pyroxene and amphibole, those are other groups of minerals. In fact, they're more than just one mineral. So the amphibole is a type, like hornblende is an example of an amphibole. For pyroxene, we talk about things like augite, and so augite is a form of pyroxene. And olivine, in fact, so there's an entire group of minerals. It depends on how much iron or magnesium is incorporated into it, but olivine actually forms first. So if SiO2 is the simplest formula, the olivine is the one that tends to form first out of a magma. So almost all of the silicates have to come from magma. And so magma is molten rock, essentially, and nature distills it in certain ways. And so the first element that forms out of a magma, olivine. Boom, right there. It's Mg2 SiO4, or Mg plus iron, Fe, and then SiO4. So it is what we call a silica tetrahedron that attaches to a metal ion, to two metal ions, in fact. So either iron, magnesium, or a combination of the two. That's olivine. Oxides are pretty important as well. So they give us some really hard minerals like hematite and magnetite and corundum. Corundum, as sapphire and ruby. Depending on the sorts of impurities in those substances, corundum can either be blue or green, yellow. It can be red, like a ruby. So those are all things that are called corundum there. Magnetite, all of these are oxides, in fact. So corundum is associated with aluminum, all these cations, right? So the cations will attach these things. Iron is what forms hematite. Now, hematite's the softest of these oxides, in fact. Leaves a streak, in fact. You're going to learn what a streak is here in just a bit here. Sulfides have a combination with sulfur. And so those are things that give us metals. And so you can take pyrite and turn it into a mineral. And so pyrite, in fact, can combine to form what we call I've got the wrong formula here. But anyway, it's like I'll get that corrected before we. Let me talk about galena here. So that's PBS, in fact. So PB is plumium, or the modern word for that is lead. And so they used to use lead for plumbing in the Roman Empire, and so it was called plumium. And so PBS is a plumium sulfide or lead sulfide, and so you drive off the sulfur by smelting it, and so you can get lead from that, right? And so that's what galena is. And so pyrite is an iron sulfide, and so an iron sulfide Fe course that we offer. And so Geology 113 here is just an introduction to the lecture part of this course, and it's Geology 114 that you'll get the lab experience in there. So you may have to take that in order to satisfy the general education requirements for your degree work. Okay, so sulfates are next, and so in fact the letters on here are actually related to the images that you see at the bottom down here. So I show like that's a feldspar crystal in A, and B is actually, that's a ruby there. So B is the ruby there. E is pyrite, and so you can actually see that it looks like fool's gold. And so D there is a type of D is the mineral barite there, and so that's the pink mineral in there. You can see so it's kind of bladed crystals in that one there, and so you can actually see the rhombohedral shape of calcite there. And then the last one on here is a mineral that's called apatite, not to be confused with being hungry or something like that and having an appetite. Apatite for spelling on that sort of mineral, and that's a type of phosphate. And so it is PO4 is the radical for phosphate. Carbonates CO3, halides, or anything that would be anything in that second column in, like the fluoride or other things that are in that column. So the sulfates are a radical as well, and sulfides, of course, just combine with sulfur, and the oxides just combine with oxygen there. And so those are all various types of mineral classes as well. Now, the mineral uses is the next step along the way here. And so when we talk about mineral uses, we've been knowing about these things forever. And so here you can see we started off in the Stone Age, and so we still had things that were made from natural materials all the way back to prehistory, right? In earliest Africa, there were stone tools that are found associated with the earliest hominid, types of in paleontology, you could find skeletons of in Africa, many of the earliest human being forms. In fact, so Homo erectus, Homo ergaster, there's a whole bunch of different species that have been identified based on the characteristics of their skulls and their anatomy, essentially, from the bones. After the Stone Age, we got into the Bronze Age, and that's where you have to mine copper, and you also have to mine tin. You have a little metallurgy going on, and through that metallurgy, you're able to make bronze. And so bronze instruments held up much better than copper, and tin wouldn't do anything at all, hardly. And so, because it's too thin, right? So it's like, it just forms foils, essentially. But when you combine it with copper, you can make bronze, and you can make vessels out of it, or you can make spear points and things like that. After the Bronze Age, people developed the Iron Age. And so iron was another. After the Bronze Age, people developed the abilities items, and they turned iron ore into iron, and they were able to make plows, spear points, and things like that. So the Iron Age followed the Bronze Age, and so they forged these different metals that way in order to make society better, right? And so here you can actually see that's the chemical formula for gypsum as well. So when we talk about minerals, gypsum has some great uses. In fact, every house that's built in the United States typically has gypsum in it. It's what we call drywall, right? And so plaster of Paris is a substance that you can grind it up, drive off the water that's in plaster of Paris, and then when you add the water back into it, it hardens. And so when it hardens, it forms like gypsum, right? So that's one of the uses of it. And you can layer that in between paper layers, and so you can make drywall that way. And so drywall has a few interesting properties. One of them is it absorbs sound, and so houses are made out of drywall these days rather than plaster in order to absorb sound in between, like say a bedroom and a bathroom and places like that. So it deadens the sound essentially when we use drywall in modern construction techniques. With that, there's some other ones that we use as well. So that is the use for gypsum right there. And as we continue on, we know that we can take sulfur. Sulfur can be used for a fertilizer, and it can be used in the chemical manufacturing and a lot of things. You can make matches out of it when you combine it with phosphorus. They make pharmaceuticals out of it. Everything has to be made out of something, right? And so with garnet is an abrasive, right? It's a silicate mineral, but the red sandpaper that you would see maybe at a Home Depot or a Lowe's, you would say that's going to be the red sandpaper is going to have a lot of garnet in it. And so garnet, it can be used for like jewelry as well, but in fact garnet is mostly used for abrasives. In fact, so barite is another one, or bauxite I should say. Bauxite on here is aluminum silicate. If you heat it up to an extraordinary temperatures, you can actually get the aluminum out of it. We don't do that too much in the United States because of the harmful gases that are given off in the smelting process for bauxite, but you could, they take it to other places. Mainly like Iceland, I think, is one of those places, in fact, and they make aluminum cans and things like that, aluminum sheeting. The aluminum has 1,000,001 different uses, right? Halite is used mostly for table salt or for ice removal, and so it's also used in chemical processes and things like that. Talc is another one that used to be used for cosmetics, but they've had to take it out because it had too much asbestos in it. So we don't use talc or talcum powder anymore that actually uses talc as an ingredient in that substance. Fluoride is used to weld things, and fluoride actually is a flux for welding and used in steel making as well. And so here you can see some of the images for some of these substances down here at the bottom down here. Next on the list here, galena. We get the lead out of galena, so PBS is the chemical formula. We can make bullets, batteries, shot. And these days, we mostly use bismuth for like bird shot and things like that because we know that lead is one of those things that's toxic to animals and human beings as well. And so we've taken the lead out of shot these days and used bismuth instead, another naturally occurring substance. Fishing sinkers, tire weights, things like that are all made out of lead. Sphalerite is zinc sulfide, and that's used as a coating on a lot of steels, like ships always have zinc associated with them because the zinc attracts much of the corrosion, and so you can use a zinc block to keep the metals that are if you have a ship at sea, keep it from actually deteriorating and corroding as much as it normally would in salt water. So it's used to galvanize nails and things like that, so it's more impervious to water. So when you galvanize things, it actually makes them more resistant to things like rust, right? And so you don't want things to rust, you will galvanize it. So for hematite, Fe2O3 here, magnetite, Fe3O4. That's the chemical formula I was looking for before. Limonite is a hydrated version of that, and so that's a hydrated iron oxide, so it's got some water attached to it there. Graphite, it's used for pencils here. So these are all images down at the bottom down here. And then carbonates, that's what the aggregate material is down here at the bottom. You can either use calcite or you can use dolomite there. Dolomite and calcite are like, twins essentially, except the one has magnesium in it, right? So the magnesium combines with the calcium and attaches to two of the CO3 molecules that way. And it's used for construction. You can actually turn calcite into cement as well. You have to heat it up to somewhere between 1,500 and 1,200 degrees Fahrenheit, but you can actually generate quicklime that way, and quicklime is added with sand and clay in order to make Portland cement. And so Portland cement is in our list in the view down here, and so you can actually see an iron mine then at the last down here. So those are all substances that have to be mined out of the earth. So the next phase of what you're going to learn, not in this course, but in Geology 114, would be how to identify minerals. And we use the physical properties, and I still have to tell you about them a little bit. And so hardness is one of the things that we use to describe minerals, and that's its resistance to abrasion. This is where I like to point out, even though diamond is the hardest substance known on Earth, it can cut glass with a diamond. You can actually see how resistant to abrasion it is, but in fact it's very brittle because of its chemical structure as well. So if you stepped on a diamond, it's gonna fracture it along planes of weakness. In fact, it will actually cleave, and so you can have cleavage with diamond as well. So don't step on a diamond, okay? Hardness, that resistance to abrasion, in the test that you're going to do in Geology 114, we use the glass plate test. Luster is how shiny it is. Does it look metallic or does it look non-metallic? It's a play of light, right? So it's like some substances we can say have a pearly luster, or they have a dull luster, or things like that. Those would be considered to be non-metallic. And then lastly, we have things like cleavage. How does a mineral break? For instance, quartz does not break along planes of weakness. Instead, it makes scallops, essentially, and so we call that conchoidal fracture. You see conchoidal fracture when you see things like Native American projectile points and things like that, or scrapers, right? And so you can see those scallops that develop on those tools that people made back during the Stone Age in North America and in other parts around the world as well. So the Stone Age sort of tools that people made relied on conchoidal fracture to make sharp edges, essentially. That's called fracture. Conchoidal fracture, shell-shaped is what it means. The density of an of a mineral, how hefty is it, right? What does it feel like? Does it feel heavy for its size? We have a way to actually measure that with this Jolly balance over here. So that's a Jolly balance over on the right-hand side of this diagram. And you can see on there that it has a spring on it, and there's a little, like a basket at the bottom there. You put a mineral in there and you can weigh it in air. And then you take a beaker of water and submerge the basket in water and weigh it again. And you'll get a comparison. How much water does that mineral sample displace? And so you get a comparison of what the masses of that water, of that mineral is to its mass in water. You know how things are lighter in water, right? So you can pick up a huge stone if you're in a pool, right? But if you're on dry land, it's going to be much more difficult to pick up that same stone. The water's helping you essentially, right? So how do you compare the same volume of water? And so, for instance, water itself weighs 1 essentially, whereas things like galena could weigh up to like 4. A barite is 4.5. Galena, I think, is like 7. So they weigh a lot more, 7.5. Other ways to tell what things are, not just the density, but also the color. Sometimes it's probably the least important. So some minerals can have a variety of colors, like fluorite, for instance, it can be brown, it can be yellow, it can be blue, it can be clear and transparent as well. Streak is another one, right? So we can make streaks like you can see in the second image at the bottom down here. On the left-hand side, that is a variety of hematite there. And then the second one in there is another variety of hematite. So it's specular hematite on the left. Actually, specular hematite is going to be in the middle part there. And then you can see what it looks like to have graphite or magnetite and minerals like that, in fact. So you can form streaks on a streak plate. It's a ceramic plate, essentially, is what it is. Sometimes we can drop acid on rocks in order to find out if they're made out of calcite. So calcite reacts very vigorously. You can see the third image down here at the bottom, and that's calcite reacting to dilute hydrochloric acid there. It fizzes, and so that's one of the ways to tell calcite. And that's a calcite mineral on the right-hand side over here. It has rhombohedral cleavage, so the way a mineral breaks, right? So that's a cleavage with rhombohedral. It looks like a cube that's been squeezed a little bit, right? And so it's kind of tilted to one side there. That's rhombohedral cleavage there. There's other things that we could do as well. We don't do them typically, but you can see if they fluoresce. You can see if they are fluorescent. You can see if they are phosphorescent, right? Do they glow in the dark, essentially? Are they magnetic? And so these are all things that we can do to try to identify minerals. And you're going to get to do that in Geology 114. This is not the class for that. And so that is a short introduction to elements, to ions, to isotopes, to atomic mass, atomic number, the way that things bond, either ionic bonding or covalent bonding. And so covalent, shared electrons in the outer shells, or ionic bonding, the pluses and minuses of ions, bring them together. And then you learned that some of these, up to 6,000 of them, are called minerals, these natural substances that occur. They could be native elements, or they could be minerals that combine with radicals in order to form minerals. And so, welcome to minerals. This is the stuff that the Earth is made out of. We're going to talk more about minerals when we talk about rocks next, because that's the building blocks of rocks. Not all rocks are made out of minerals, but most of them are. And so that's how we get to talk about the stuff that makes up the Earth. And so that's part 2 of this, right? So if we cover tectonics in the first part, this is a little drier, and I get that, and it's like, but if you can power through this, I'd appreciate it. And you're going to find that these things will be useful when we talk about rocks later on here. I thank you for your attention. So anyway, I hope you get to enjoy this, in fact, and so make the most out of it. And as a reminder, you can always speed these things up, so you can do a playback speed of 1.25 or something like that on YouTube. It makes it easier to go through these things in rapid order. So anyway, I will talk to you soon, and we're going to be talking about rocks next. Take care. Bye now.